All right. So we talked about last week, we talked about lines, and if you've worked through some of the homework, you should have done some work with lines. We really like lines to be written in this y equals mx plus b form. So that's really our favorite equation of a line, and this is called the slope-intercept form. And you will see some other forms listed both in books and in maybe in our textbook and even a little bit in the homework sometimes. You may see some other versions of lines, but this really is the version that I think is the most useful and that you should spend the most time with, okay, is this slope-intercept form. And when I ask you on a test or on the take-home work, if I ask you for an equation of the line, I'm really assuming you're going to put it in the slope-intercept form, okay? Other forms are okay, but this is the easiest form, and it's nice because as we notice, this first value here gives you the slope, and this b value here is always the y-intercept. Right, and those are important features of any line. They give us kind of where the line is located and then also the angle of the line. So if I give you a line like 2y plus 4x equals, let me make that 2y plus 5x equals 8. This is a line because it's a linear equation, right, in two variables. And if you want to graph the line or find its slope or really almost anything you want to do with it, we'd like to have it in this y equals mx plus b form. So I'm going to start by subtracting the 5x from both sides, and then I'm going to divide everything by 2. And I get y equals minus 5 half x plus 4. So now that information shows me, well, I can read off the information I need there, right? This is my slope, and this number is my y-intercept. Now, it just depends what the question is asking me. I may just need one of those values. I may need to graph the line. It's easy to graph the line from this information too. Right? If your y-intercept is 4, that gives me a very easy point. I know my line goes through that point. And then a slope of minus 5 halves. Remember, the slope is always the rise over the run. So that tells me it goes, if I go down 5, that's the negative 5, and I go over 2, I get another point there. That point there, 1 second. That point there is my second point on the line, or another point on the line, and I know that the graph or all the solutions then fall through that process, right along there. So that's a really handy way to graph a line. I don't have to plot points. It's much less likely to make errors typically when you're using that information. So, right, we take the line, we kind of try and put it into this form, and then from that form I can graph it. Right, so today I want to talk about some more equations of lines. We have kind of two directions. Sometimes we're given the equation and we want to find information, whether it's a graph or the intercepts. And sometimes we have information and we want to come up with the equation, right? So that's what I'm going to work on a little bit today, is how do we come up with the equation of a line?
I also have a question.
Yeah, great.
After you're done with that problem, can you also show me how more examples of functions or domain range and piecewise
Yeah,
functions like that?
I will do that. So I'm gonna lead towards that. So I'll do a little bit
Oh,
here with
okay.
equations, and then I'll get, because that is kind of the middle section of this is working with functions and
Okay.
piecewise functions. So yes, that's a good question. If I want to find the equation of a line, to find an equation, we really need the slope and the y-intercept. If I have both of those things, the slope and the y-intercept, I can just plug them right in, and that tells me what the line is. Now, I'm not always given that information, so I have to kind of be able to find it or calculate it. And so one common way is to use what's called the point slope form, which is this: y minus y1 equals m x minus x1, where m equals the slope and x1, y1 equals a point. So if I have a slope and a point, I can use this new formula to figure out my equation of a line. The problem with that formula is then you have to remember, it's not too bad when you have a note sheet, right? You can write it down, but you've got to use that formula. So I don't force people to do this. You can also find that information from the y equals mx plus b. So I'm just going to do an example with kind of both of these. You're welcome to choose whichever you find easiest. So here's an example. Let's find the equation of the line with the slope equals 2, and it goes through the point 4, 1. So remember here, I don't know what the y-intercept is. I have a point, but this isn't the y-intercept, right? This is just some other point. So I need to sort of calculate or find that y-intercept. I can do it using this equation here, this point slope form. Y minus y1, y1 is 1, equals my slope 2, x minus x1. Now I just have to do a little simplification to get that in the right form. So that's the kind of standard or straightforward approach there when you have a point and a slope. If you don't want to use or remember that formula, you can also do it just with using y equals mx plus b. And the way you do that is sort of similar. I say I know the slope is 2, so m has to be 2. And I also know it goes through this point. So the y value has to be 1. The x value is 4. And whatever b is needs to make that equation true. Because remember, that's what a point on the line is it's a spot where the equation is true. So this is a way of figuring out or solving for b. So I got 1 equals 8 plus b, so b equals minus 7. Now I have the information I need, and you can see if I plug in the slope and the y-intercept, I'm going to get exactly this equation here. It takes I don't know, I mean, a tiny bit of extra work, excuse me, because you have to plug the things back into the y equals mx plus b. It's not really very much extra work, right? But it is a little extra step that you have to take to make sure you have your answer in the right spot, okay? But this is one of these is the strategy that you should use when you're finding the equation of a line, okay? If you are comfortable with this one, that's kind of my standard way, but I have a lot of students that are successful just focusing on that version. Either one is fine with me. Okay. Any questions on that?
Yeah, can you zoom out with the camera so that I can screenshot that?
Yeah, can you see, what can you see right now?
Like half the paper.
Like you want the whole paper.
Yeah. Awesome. Thank you.
Try. I can also scan these afterwards and post them.
Ooh, okay, that works.
I'll do that. I'll scan these sheets and post them on D2L.
Okay, thank you.
So, okay. One second. I'm sorry. Okay, I'm back. So what we have here is we have some other versions of these problems. They don't give you always the point and the slope like that one, but they'll always give you enough information to find the point and the slope. Okay, so for example, sometimes you'll see the equation of the line through maybe 2 points, 1, 4, and 3, -2. So here the difference is we have 2 points, we don't have a slope, but you should remember how to find the slope, right? So from these 2 points, I can find the slope, change in the y values over change in the x values. That's just a 1. So -2 - 4, 3 - 1. That gives me -6/2, which is -3. So now I have the slope and I have 2 points. I just need one of these points. So I can pick either of them. I pick the easiest one. That one doesn't have any negatives, so that's a little easier to me. And now it's the same process, right, as before to find the equation. Another way, find the equation parallel to y = 3/2 x - 2 through -1, 2. So again, this one is stated a little differently, but if we remember or know what a parallel line is, remember parallel lines are moving at the same direction, same angle, so they're going to have the same slope. So saying that it's parallel actually means that its slope is 3/2, right? So I have to kind of read that information from this line. And then again, I have a point and I have a slope, right? Same process from there. So there's different looking variations, but in the end, they really are all the same question, finding an equation from a point and a slope. Okay, any questions? Does that feel, yeah, go ahead. Anything feel manageable? I mean, as always, it's like it always usually like feels pretty good when you watch it. You're like, okay, that makes sense. But you know, doing it on your own obviously is a little different, right? And that's what the homework is for, to help you practice that and work towards that. So I also wanted to make sure I talked about functions today. You have kind of 2 of your homework sections are on functions. A function is a relationship between 2 sets where each element of the first set, which we're going to call the domain, is paired with exactly one element of the second set, which we're going to call the range. Okay. So a function is a thing that connects. It's a relationship, and it connects two kind of sets together. And so, you know, mathematically, we often just call the x's the domain the x's, and the ranges are the y values. So like they're just x and y. But of course, in real life, x and y might be, you know, it might be your height and your shoe size, right? Or there's some relationship there. Might be the years that you spent at the company and your income, right? Those might be the relationship. So there, imagine x and y are two quantities that we care about, and the function is the way that those two quantities are connected to each other. But in order to be a function, each element of the first set can only be paired with one element of the second set. And so what that looks like, if we call this the domain and this the range, we have a bunch of things, right, in the domain and a bunch of things in the range. A function has to have each element of the domain can only go to one element of the range. It's okay if you can have, that's okay. I can have all of those elements of the domain go to that same value. That's fine. That's still a function. That's still a good relationship. If, on the other hand, I have one element of the domain that connects to multiple things in the range, that is not a function. Okay, so there's a direction here. We think of the domain as going to the range. And we often also think of these or talk about these as the input is the domain and the output is the range. Right? So kind of like a machine, right? You put something in, it spits something out. So we have an input and an output. And there's lots of different ways of representing these relationships. So this is one way, like it's called a mapping, right, where one thing kind of connects to the other. But we can also use ordered pairs to represent these relationships. So here's another relationship, 1, 2, 3, 4, 4, 5, 7, 1. So what this is this is connecting some elements x to y. So each of these is like a connection, like up here. 1 goes to 2, 3 goes to 4, 4 goes to 5, and 7 goes to 1. And the question is that a function? And this one is, because each x value only has a single y value. So this is a function. Whereas this is not. The problem is not that 1, 5, 2, 5, and 3 goes to 5. That's fine. The problem is here 1 goes to 2 and 1 goes to 5. That's not okay. This is not a function. Now for each of these, it turns out you can do it whether it's a function or not, although we really usually only care for functions. These have a domain and a range. Okay. So in this case, when I list the ordered pairs like this, the domain is just going to be a list of the x values or the inputs. So in this case, the domain is just 1, 3, 4, and 7. 1,
I have a
3.
comment. So as long as like the domain, which is the x or x-axis, as long as it's different, then it should be
Should
good
be a
as a
function.
function.
That's
But
right.
then if it's like the same function as like in the x-axis or x, then it wouldn't be.
That's right. So you
Okay.
can, yeah, you can see it from these ordered pairs. As soon as you see a repeated x, that's a clue, like that says that's not a function, because that
Okay.
one x shouldn't appear twice.
Okay.
Yep.
How about the y? Can it repeat twice or
Good
appear?
question. It's okay. So like this, like if I looked at this as an ordered pair, all of these would have the same y value, and that's okay. That can still be a function. Okay? Like when I look at this bottom example, it's okay that all of these end in a 5. That's fine. No problems there. It's only these two, that's why it's not a function.
Got
Okay.
it. Thank you.
So yeah, it's only the x. There is a direction there. The x's are different than the y's. And if you had some repeated y values, you wouldn't have to repeat them when you wrote the range. You just need to indicate what possible outputs are there. For this one that I have, this top one is 2, 4, 5, and 1. And you can write it in any order, 2, 4, 5, and 1. So the questions you're asked in these sections are typically, number 1, is it a function? And then number 2, what's its domain and what's its range? Okay, so that's how you can sort of look at it and identify it, talk about domain and range from this representation. Okay, so these are ordered pairs. That's one way to write a function. Those were excellent questions. Any other questions about this? Let's take a look at another representation, and maybe that'll help. Okay. Here's another. This is a Cartesian coordinate plane, and let's look at this graph. Let's say it stops there. Okay, so those are a solid circle where it stops. So this is a different representation. It's not a list of ordered pairs, but it kind of is a list of ordered pairs, right? Because we remember that the points here are all ordered pairs, right? Each of these is an ordered pair. And so the question, this also creates a relationship between the x's and the y's. And so we can ask the same questions. Is this a function? And what's its domain and what's its range? So if I imagine each of these as being an ordered pair, an x, y, can you see that for this function, every ordered pair has a slightly different x value, right? The comment before was like, well, if we have 2 of the same x's, then that's not going to be a function. But here, no matter what x value you tell me, there's only one point for that given x value, okay? So this is going to be a function. And the way we can see that or kind of work with that in general is called the vertical line test. So visually, each kind of fixed x value is a vertical line. And every vertical line there only touches the graph once. So vertical line test only touches the graph once. That implies that we have a function. So that's a really nice way of checking whether a graph is a function or not. If a vertical line ever hits it twice, then you're going to have a repeated x value and it's not going to be a function. Okay. So the second part here is what is its domain and what is its range? So the domain are all the x values, and you know, my graph is not perfect. Graphs are always a little bit of an estimate, right? But here's what I can't do. I can't say my domain is -3, -2, -1, 0, 1, 2, roughly 3. That's not correct, because it's also all of these other values in between there, like a half and -7/8, and everything else in this range is also part of the domain. I can't list those, so I need to write those as an interval. So an interval, remember, is like all the values between 2 points. So my domain goes all the way down to -3, and I include -3, and then it goes all the way up to +3, and I'm going to include +3. So this notation or way of writing includes every single value between -3 and 3. That's very different than what I wrote here, right? I just scribbled on. This is just 4 numbers, 1, 3, 4, and 7. This is infinitely many numbers. Big difference, right? This is everything between -3 and 3. So we want to keep that straight when we need discrete values, which are these, just a couple. I can just list them. If I got 5 or 10 or whatever, I can just list them. And then this, which is called a continuous set, which is a whole range of values. In the range, we can play kind of the same game, but the range, remember, is the y values. So rather than going from -3 to 3, for the y values, I'm going to start here, which is -2, and go up to, looks like 3 there. So the range in this case is going to be -2 to 3. And again, we can see that there's, you know, in our list of ordered pairs, there's going to be 2 y values, or sorry, 2 of the same y value, but there's certainly from different x values. So that's okay. We can have repeated y values. We cannot have repeated x values. So another example here is where we might have something like, let's try this. And, you know, maybe this graph goes on, maybe it doesn't stop. So this is a relationship, and then the question is this a function? Well, some vertical lines are fine, right? That just touches it once, but I can certainly see there's a lot of vertical lines, and all it takes is just one. Here's a vertical line that hits the graph in 3 spots. Definitely not a function. Okay, so once you get that vertical line, it's you know, pretty straightforward no matter what the equation is to try and determine if it's a function or not. Any questions about those examples? There was also a question about what's called a piecewise function. So I'll introduce that. That's a little bit of, in this nonlinear function, section 6, and that's fine. You should be kind of working towards that. But it's very much related to this idea of domains and ranges. Piecewise function. And piecewise just means like it's defined in chunks. So a lot of the functions we looked at are defined kind of the same way everywhere, but in reality, that's not always the way the world works, right? Like if you use electricity at a company, Xcel Energy charges you different rates depending how much energy you use. So for the first bit, you're charged at some rate. But if you go over that, all of a sudden, you're charged at some different rate. So we want to be able to represent that idea, which is a piecewise function. It's where you have these sort of jumps or sudden changes, and we can create that. A lot of the challenge for students is just understanding the notation, which is like, how are we writing? What do we mean by the symbols that we write down? So here's an example of a piecewise function. Oh, see, and I forgot, before we can even jump into piecewise functions, I knew there was something else within functions. We've got to be comfortable with function notation. So how do I write down functions? So we're going to say piecewise functions, talk just briefly about function notation. Function notation is replacing y with this symbol f of x is what we call it. F of x. And we can do that when we have a function because the y value is totally determined by the x value. You may believe what I'm saying, but it probably is going to take some time to like really connect what that actually means, right? I can say it and you can trust me, but like I don't know that creates any actual connection there, right? Until you work with a little bit. So the idea, the sort of nuts and bolts idea is that instead of writing the y, we can instead write it with this symbol f of x. And it actually has some real advantages. So like this is a function, y equals 3x plus 2. This is another way of writing a function. It's an equation. And we know that equation is going to generate a line of solutions. And it turns out that line is going to be a function, right? Because it's going to pass this vertical line test. It's going to look like this, right? 2 is there, and 3/1 is the slope. So you're going to get a line that looks something like that. Very clearly passes the vertical line test. This is a function. What we are going to do instead is we're going to write that same relationship, but instead of y, I'm going to write it as f of x equals 3x plus 2. And the advantage, the big advantage here is that this notation makes it easier for me to connect the x's and y's together. All right, and that's really what I want out of this function idea. So what I can do is I can give you an x value and sort of compute the function at that x value. So for instance, f of 1 is saying what is the x value? What is, if the x value is 1, what is the y value? And we can do that by just plugging in the 1 here into the x. So we get 3 times 1 plus 2. So notice what I did is I just replaced the x value here of 1 with this value 1, and I did my calculation, and that spits out 5. So what that's doing is that's giving me a point or an ordered pair, right? Which is, this is the x value, which is 1, and this is the y value, which is 5. And I can do that for any x value that I want that's in the domain. You could do the same thing over here. It's just you have to actually say what the x is. Right? So this tells us what we want in a more kind of direct way. Okay? It's not changing the relationship at all. It's just changing how we write it. And the key thing is that whatever I put in here for x, f of 2, I just plug that right into my formula. 3 times 2 plus 2. So I don't need that extra parenthesis there, right? But 6 plus 2, that would be 8. Okay. So for this given relationship, I can calculate at all these different values. F of x is the symbol that I use to keep track of that. Okay, it doesn't mean F times x or anything like that. It's just a way of writing y, but it has some nice advantages for us. Any questions about function notation?
No.
Okay. It's one of those things that, like, when you get it, when it clicks, it's pretty easy. Like, there's not that much to it. But when it doesn't click, it feels impossible, like a foreign language, right? And very confusing. So I think that's that's a good lesson for everybody, is it's not about whether a topic is easy or hard. It's just whether it makes sense to you or it doesn't make sense to you, right? If it doesn't make sense, then it's really hard and confusing and frustrating, right? So I think sometimes students are all worried, like, oh, that should be easy. Well, it's not easy if it doesn't make sense, right? And vice versa. I think things that are hard, they don't have to be, right? As soon as they make sense, they cease being hard, right? So, but this is definitely one where it's like, as soon as you get it and see what it's trying to say to you, all the problems will go pretty smoothly from then on. Okay, so now we're ready for a piecewise function. So rather than writing f of x as just 3x plus 2, this function is defined this way no matter what x I put in, right? I put in 17 or negative 23 or anything, and I get the same formula, right? That's what this function says. So over here, I say f of x equals, now a piecewise function is going to be defined differently. So I might say f of x is going to equal to 4 if x is less than or equal to 1. Sometimes you'll see an if in there, sometimes you will not. Another formula might be f of x equals x plus 3 if x is strictly bigger than 1. And again, I might write it with an if in there, or you might see it without that if. This second part here is telling you which of these two formulas to use. Remember, it's a function, so if I give you an x, there can only be one y. I can't have an x being two different things. Okay? And I have to choose one of these, because that's the way a function works. This formula is going to tell me which one of these to choose. So if I try f of 0, my x value there is 0, and 0 is certainly less than or equal to 1. So since that is true, that tells me f of 0 is 4. It cannot also be 3. That's definitely not possible, because they can't be both things. F of minus 1, same thing. That's less than 1, so I'm using this top formula, which in this case is 4. F of 2, now all of a sudden that 2 is not less than or equal to 1. 2 is bigger than 1, so that means I'm going to use this other formula, which says 2 plus 3, right? And that gives me 5. F of 3, okay, 3 is bigger than 1. 3 plus 3 is 6, okay? So that formula is what is how we use a piecewise function.